Hello friends, in this video lecture we are going to discuss the surge impedance and surge impedance loading. So let us begin. We are discussing the voltage stability analysis, or else we can say we are discussing the voltage stability topic. So here let us discuss in this lecture the point called surge impedance. Okay. See, what is the importance of this surge impedance loading? First, let us try to understand this. The surge impedance loading, actually it is used in prediction of maximum loading capacity of the line. Okay, so this is where the surge impedance loading is used, and that is why it is important. Okay, at the end of this lecture, while discussing the applications of the surge impedance loading, I'll discuss this point with you. Okay, because in power industry, while describing the power loading capacity of any line, the power engineers uses this term surge impedance loading. Okay, so before we actually discuss what is surge impedance loading, let us first discuss the surge impedance. See, to understand the concept of this surge impedance, let us consider a long transmission line, okay, whose length is, let's say, greater than 250 kilometer. Okay, line having length more than 250 kilometer comes under the long transmission line. Okay, now as per the inherent property of the long transmission line, we know that the capacitance and the inductance are distributed throughout the length. Okay, so as for this long transmission line, as the capacitors and inductors, they are distributed throughout the line, so we represent the long transmission line this way. Okay, let's say we have considered some portion of the line. Okay, here I'm representing the capacitor and inductor, okay, in a distributed manner. So now when this line is charged, okay, when the line is charged, let's say at this is the sending end, so we will have here Vs, and let us say this is the receiving end. Let's say we are having the voltage here as a Vr. Now when it is charged, the capacitor, what it does, it start generating VAR. VAR is nothing but the reactive power. Okay, so when the line is charged, we can say that the capacitor will be generating the reactive power. Okay, and that reactive power will be consumed, or it will be absorbed by this inductor. Okay, so now if suppose if that generated VAR, okay, I can write here as it is the capacitive generated VAR, if it is equal to inductive VAR consumed. Okay, so now for the capacitive VAR generated, we can write it as V square upon XC, and the inductive VAR consumed, we can write it as I square XL. Okay, here this V is phase voltage, I is line current. Okay, this XL and XC, XC will be capacitive reactance per phase, and that XL is inductive reactance per phase. Okay, so now from this we can write it as that is V square upon I square is equal to XC into XL. Okay, again, if I take the square root on both the side, so we will get V by I is equal to square root of XC into XL. Okay, now we know that XC we can write it as 1 upon omega C. Okay, whereas again we can write it as omega, we can write it as 2 pi f into C. Okay, again, as we are considering a long transmission line where the capacitor is distributed throughout the line, so we'll multiply it with a L. Okay, that is the length of the transmission line. Again, XL we can write it as omega L, or else we can write it as 2 pi f L. Again, let us multiply it with also length of the line. Okay, so if I replace this XL and XC with these values, so I'll get here as V by I is coming as, it is equal to, for XC let us first write, we get XC as 1 upon 2 pi f L C. Again here on in the numerator side, or on in place of XL I can write 2 pi f L into this small l. Okay, so again here you see this 2 pi fl and this 2 pi fl will get cancelled, so we are left with here as V by I is equal to square root of L by C. Again, if you look at on this left hand side, the V by I, as per the electrical property, this is nothing but the resistance. Okay, so I can write it here as V by I, let us denote it with the ZS, that is nothing but equal to square root of L by C. Okay, so this is called as the surge impedance. Okay, so sometimes this is denoted as ZS or ZC. Okay, ZS or ZC, it is we can say that here it is the characteristics impedance, it is the characteristics impedance of a lossless line, a lossless line. Why we are seeing it as a lossless line? You see, the reactive power generated in this line is absorbed by the line itself only. Okay, so net reactive power in case of this line will be zero. Okay, and we know that the voltage problem comes when there is a problem or when there is a flow of reactive power. Okay, so as there is a net reactive power is coming to be zero, so there will not be any problem with the voltage. Okay, so in this case we can say that as we are going to absorb the generated reactive power, so losses will be zero in that case. Okay, so that's why it is also sometimes called as the surge impedance. Sometimes it is also called as the characteristics impedance of a line, okay, having, which is a lossless line. Okay, so that is what idea of the surge impedance. Now let us try to understand what is surge impedance loading. Surge impedance loading. Okay, it is actually the power delivered, we can write it here as the power delivered by a line to a purely resistive load which is equal in value with surge impedance. You see, as the capacitive effect and inductive effect are going to nullify in case of the surge impedance, so we can say that whatever loading will be there in that case, that will be a purely resistive loading. Okay, and the value of that is equal to the surge impedance. Okay, so surge impedance loading, sometimes it is denoted as SIL. It can be calculated as SIL is equal to root 3 into VR into that current, receiving end current, we can write it as VR divided by root 3 into ZS. Okay, so if I simplify this root 3 will get cancelled. So we're left with this VR square divided by ZS. Okay, so this is how the surge impedance loading is calculated. Okay, again, you see, if suppose if the line is terminated by this surge impedance loading, okay, if the line is terminated by SIL, okay, or else we can say that the loading is equal to the surge impedance loading. In that case, losses will be zero. Okay, as the losses are going to be zero, so for that we can write that the sending end voltage is equal to receiving end voltage. Okay, so as we are going to obtain this, so we can say that this will give the flat voltage profile. It gives the flat voltage profile. Why? Because the losses will be absent in that case. Okay, so for this, if suppose the line is terminated by surge impedance loading, okay, now suppose let us try to draw some different graph of this VS and VR for different loading condition. Okay, let us see how that graph will come. Okay, let's say on this side we are having VS and on this side we are having VR. Okay, now this is Vs. Now you see, for no load condition, for an uncompensated line, okay, we will get voltage in this fashion. Okay, again, for surge impedance loading, okay, if the loading, if it is equal to surge impedance loading, then we will get a flat voltage. Okay, we will get a flat voltage, or else we can say that the sending end voltage is equal to receiving end voltage. This is no load condition where the receiving end voltage is greater than the sending end voltage. Okay, again, this is the full load condition. Okay, where the receiving end voltage will be slightly depressed with respect to the sending end voltage. Okay, again, we can have one more condition. Suppose there is a short circuit. Okay, dead short circuit. So at that time, the receiving end voltage will become 0. Okay, so if I write here, this is for no load condition, this is for surge impedance loading, and this is for full load condition, and this is for the short circuit condition. Okay, again, the surge impedance, what formula we have got for surge impedance, that ZS is equal to square root of L by C. Okay, so it is independent of the length of the line. So I can write here as ZS is independent of line length. Okay, as it is independent of line length, SIL, surge impedance loading, will also be independent of the line length. Okay, and with that we can say that the voltage, that is the relationship between the receiving end voltage and the sending end voltage, will also be now independent of the line length if the line is terminated with the surge impedance loading. Okay, so now this is all regarded to the uncompensated line. Now if we have the compensated transmission line, then in that case, that surge impedance loading, it can be written as, so let me write here, for compensated line. So this surge impedance is denoted as ZS dash. Okay, it is calculated as ZS into square root of 1 minus KCSE divided by, it is 1 plus KCSH into 1 minus KLSH, where this ZS we know it is the surge impedance of an uncompensated line. This KCSE it is actually the percentage series, see SE indicating series and this capital C indicating capacitive compensation. Percentage series capacitive compensation. Similarly, this KCSH, it is nothing but percentage shunt capacitive compensation. Again, that KLSH is percentage shunt inductive compensation. Okay, so this KCE, KCSH or KLSH, they can be calculated with the help of the formulas. KSE is nothing but 1 upon omega square, okay, length of the line, then value of the series capacitor. Then this KCSH is nothing but CSH divided by C, and that KLSH is calculated as 1 upon omega square length of the line, then value of the shunt inductance. Okay, so this is how we can calculate the surge impedance if the line is compensated. Okay, now we have got the idea what is surge impedance and what is surge impedance loading. Let us discuss the applications of the surge impedance loading. Okay, see this basically if we talk in terms of the voltage stability, this is very important. If you want to maintain the flat voltage profile, then in that case we can go with the surge impedance loading. Okay, so now we are going to discuss the applications of this surge impedance loading. Okay, where it is going to be useful. So as I said in the beginning that the power engineers, what they do, basically they describe or they represent the loading in terms of this SIL. Okay, so I can write here line loading is represented in terms of SIL. Okay, suppose let us take one example. Let's say for short line, for short transmission line, okay, whose length is less than 80 kilometer. Okay, in uncompensated condition, loading on this short transmission line, if we can load it in this range 1.2 to 1.5 times the SIL. Okay, so this can be the loading for the short transmission line in uncompensated condition. Okay, let us take in any voltage level and let us calculate what would be the loading on this line. Okay, let's say for 110 kV, for example 110 kV. Okay, so let us calculate the loading of the line. So as I said, SIL we know how we can calculate. Let's say we are going with 1.5% of SIL. Okay, so 1.5 times of SIL. SIL just now we have discussed, it is nothing but VR square divided by Z. Okay, again we know that for overhead line, that is OHE, we have the resistance as 400 ohm, and if it is a ground wire or if it is a ground line, then we have the resistance as a 40 ohm. Okay, so let us consider that 400 ohm and the voltage level is given 110. So it is 1.5 110 kV bracket square divided by that 400. Okay, so if you solve this, we will get the value around 45 megawatt. Okay, so this 45 megawatt, it indicates we can load this short transmission line with this much of power. Okay, or we can deliver this much of power with the help of this short transmission line. Okay, again we can take any line, and for that voltage level we can calculate the loading of that line. Okay, so that can be the one application to get the loadability, means how much load we can put on the line, that we can calculate. Okay, again, the second what I can say is, let's say for a particular condition we get to know the loading. Okay, how much the power is to be delivered using that transmission line. So accordingly we can decide the number of conductors, okay, or else we can say the number of circuits we can decide with the help of this surge impedance loading. Again, so let's say we know what is the loading requirement or what is the power to be delivered. Now from that, with the help of this formula, let's say this is the loading. Okay, if we know the loading, okay, and we know the impedance, so we can decide at what value of the voltage we can go for this loading of this transmission line. Okay, so that is also with the power engineers to decide, okay, at what voltage level they want to load that particular line. So this thing we can do with the help of this surge impedance loading. Okay, again, one more application it has got. It can be useful in deciding the sizing of the lightning arrestor. Okay, so this is all regarding the surge impedance and surge impedance loading. Thank you very much.